Our final rocks lecture here is on metamorphism. So we finished up igneous rocks, sedimentary rocks. Now we're going to finish up with metamorphic rocks. So this is another one that's designed for you to take the quiz as you complete this lecture, which you can find in week 3 assignments folder on Blackboard. So I'm going to start with the same figure from before. We've talked about igneous and sedimentary rocks. Our final one is metamorphic rocks. If we're looking at where metamorphic rocks can form, they tend to mostly form around magma chambers, and then when you have two tectonic plates that are colliding, so you get it in mountains, and then you get them around magma chambers. So what is a metamorphic rock? This is an example of one. This is called gneiss, Gneiss, which you'll see later on. But it's a rock that formed by pressure and temperature, the combination of pressure and temperature, or just pressure or just temperature, as we'll talk about here shortly. So you either have a change in one of these factors or both. So metamorphism is due to changes in temperature and pressure or stress. The way that you can think about this is in metamorphic rocks can be kind of confusing because they start as a solid and they end as a solid and they never turn into liquid. And they will change totally without ever having changed away from a solid. So basically heat and pressure can change the rock. If you're kind of watching through here on the right side, we have this convergent boundary where there's a lot of pressure. Pressure can kind of squeeze rocks and add stress to them and make them change shape. So a good example of this is, let's say you just have a regular old sandwich. You add some heat and some pressure to it, like in a panini. Now your sandwich looks a little bit different. It's got the nice little scorch marks on it, basically, and it's been flattened. So it stayed solid the entire time, though. Starts as a solid, ends as a solid, but you have added heat and pressure and you've created something new. Now out of your lame sandwich, now you have a panini. So how does this happen? You can get either one of two things. You can get a change in the minerals in that rock. So you can start with something, we call it the parent rock. So that's the original rock that existed. This is shale. Shale is made of mud, as we talked about in sedimentary rocks. So this is shale. And let's say you metamorphose shale. Shale can turn into a rock that we call gneiss. And what will happen is that the minerals change. So what that means is that gneiss over here, these kind of red splotches, which are a little bit hard to see, those are minerals called garnet. Garnet does not exist in shale. Garnet can only exist in metamorphic rocks. So you get a change in mineralogy. You start with a certain mineral, and then it turns into a new mineral under the process of metamorphism or through the process of metamorphism. You can also get a change in texture. That's another option for metamorphism. So you can start with a parent rock. This is limestone in this example, and limestone can have fossil fragments in it. And limestone is made of calcium carbonate, so CaCO3 is its chemical formula. Marble, which is a metamorphic rock, is also made of calcium carbonate, CaCO3. So the only difference here is the change in texture. You've gone from these rounded fossil fragments, and they've kind of formed into this new type of interlocked puzzle piece type texture, but the minerals haven't actually changed from the original rock to the metamorphic rock. So just as an analogy, if you take a monarch caterpillar, which likes the plant milkweed, if you take a monarch caterpillar, over 4 weeks, that's going to turn into a monarch butterfly. But if you take a parent rock like shale or limestone, for example, it might take it thousands to millions of years for it to turn into a metamorphic rock. So let's talk about metamorphism and stress. So there's different types of stressors that can be enacted on a rock or placed on a rock. And if you put different stress and pressure on a rock, it's going to look totally different depending on the direction of stress or the direction of pressure. So let's say you have a circle here or a sphere that's supposed to correspond to an undeformed rock. So we'll call it equant. So equant just means that it's shaped like a sphere. It's equal, equant on all sides. Let's say that I take that sphere and I stretch it out. So I've elongated that sphere and I've formed these different looking mineral grains based on the stress that I've applied to it. Instead of adding stress by pulling on opposite sides of this equant grain, I could flatten it like a pancake from a different direction, and then form something like this one down here where you have this more pancake shape to it. So the point here is that basically what type of stress you put on a mineral or a rock determines what it looks like after metamorphism. So as an example, this is a rock that has undergone compression. So it's been squeezed from both sides, and the fact that it's been squeezed from both sides, it has made those minerals kind of line up in these kind of flat, layered approach or pattern. So based on this, there are 3 types of stress that you can add to rock. So let's say you have an unstressed cube of rock. There's 3 types of stress that you can add to that rock. So you can add tension, you can add compression, or you can add shear. So based on this diagram, you should be able to answer questions 1 through 3 on the quiz and then come back when you're done. Okay, so just like with the other 2 groups, with sedimentary and igneous rocks, we still have categories of metamorphic rocks. There are actually a lot more categories of metamorphic rocks, but I don't want to bog you down with all of them, so we're just going to talk about 2. One is called contact metamorphism, and the other is called regional metamorphism. So contact metamorphism is associated with volcanic magma chambers, and then regional metamorphism is associated with convergent boundaries, and I'll go through each of these here in a second. So let's start with contact. This one's a little bit easier to understand, and then we'll move on to regional. So what contact metamorphism is that you have rock, and that rock all of a sudden comes into contact, which is why it's called contact. It's also called thermal metamorphism. So rock comes into contact with a heat source. Usually a heat source is going to be magma. That's usually the main source of heat that we have beneath the surface. So if you have a magma chamber of a volcano, what will happen is the solid rock that's kind of around the walls of that magma chamber, they get heated up through contact metamorphism. So you have that heat source, and it kind of, for lack of a better term, it basically bakes the rock and turns it into a different type of rock in response to that heat source. So where contact metamorphism happens is kind of this zone that's a little fuzzily shaded around the edge of this magma chamber. That's where contact metamorphism tends to happen. So as an example, the redder colors here indicate a magma chamber. So if you have rock that is right adjacent to that magma chamber on the outside of that heat source, what will happen is that the more heat you have, the more likely it is the rock is to turn into a different rock. An example of this is if you're familiar with how porcelain is produced. So if you start with clay, you heat it up a little bit, you can get brick, but if you heat it up more, you can get pottery. And if you heat it up even more, then you can get porcelain. Same thing, you can take a rock, you can heat it up a little bit, it'll turn into a different rock. Heat it up some more, you'll get something else. Heat it up a lot, you'll get something else. And why I use the baking analogy is that if you take a ball of dough, it's a solid, you heat it up, it's going to turn into something else in response to that heat. So when we're looking at contact metamorphism, there's just one rock example that we're going to talk about. What happens here is that the minerals don't change at all. So you can take limestone, which is sedimentary. It's either from caves or it could be like a coral reef deposit or made of shells. It's calcium carbonate is its chemical composition. And then if you heat up limestone, so just take a chunk of limestone, take a cave deposit, heat it up. What it turns into under metamorphism is marble. Marble is also calcium carbonate. It's the same exact chemistry as limestone. The only difference is the texture is what changes between these two. So you take limestone, you heat it up, it will turn into marble. Same as taking bread, dough, heat up that dough, turns into bread. So in terms of the kind of mechanism that occurs internally to the rock, if you start with limestone and then you heat it up, what it will do is kind of make those crystals do what's called recrystallization, and they'll actually just grow a little bit larger. So this is what limestone would look like if you put it under a microscope, and then marble on the right side. So it's just got bigger grains, which we call recrystallization. All right, just to reiterate where this can occur. So let's say you have a magma chamber and you have limestone. Limestone heats up into marble when it comes into contact with that heat source. There's other examples. So if you are curious, you could take sandstone. If you heat up sandstone, you get a rock called quartzite. And if you have shale, which is made of mud, you heat up shale, you can get a rock called hornfels. So all three of those are metamorphic. Hornfels, quartzite, and marble, those are metamorphic rocks that form around the edge of a magma chamber through contact metamorphism. Okay, so your task now is to describe in detail how marble forms in terms of what the parent rock is, what environment it forms in, and what changes happen internally as it transforms into a metamorphic rock. All right, feel free to return when you're done with that quiz question. The other part of metamorphism that we're going to talk about is regional metamorphism. So it's called regional metamorphism because it occurs over a very large area. It could occur over 500 to 1,000 square mile area. So we're talking about entire mountain ranges is what regional metamorphism is. So if a mountain's forming due to continental collision, so two continental plates are colliding through plate tectonics, you will get increased temperature and increased pressure that will occur when those mountains and those tectonic plates are colliding with each other. So when these occur, it produces something called foliation. Foliation basically just means you have lines or a linear pattern to the minerals that are in a rock. So it either shows up as kind of banding, like a light and dark banding, like this example of a gneiss right here on the right side, or it'll have kind of like papery like layers in the rock, which I'll show you some pictures of that here in a second. So just to show you an example, we have a convergent boundary here. This is an oceanic plate at this point in time. This is a continental plate at this point in time, and they're colliding with each other. So we have a collision. Point A, if you watch what happens to point A, before the collision, it is on the surface. It's at a pressure of 1 bar, which is what you would be feeling right now in your own home, but you're used to it, so you don't feel the weight of the atmosphere pushing down on you. It's just to give a baseline number, and then temperature about 20 degrees Celsius. So let's say those plates keep colliding. That point A, which was on the surface, has now gotten pushed down about 15 kilometers beneath the surface. The temperature has gone up to 450 degrees Celsius, and the pressure is now 6 kilobars, so it's 6,000 times greater than when it was at the surface. So when we have two tectonic plates that collide, these collisions create high temperatures, create high pressures, and you will get this rock, metamorphosed rock that will form. So here's a visual for you. It's grainy, but we have this collision between two continental plates. And if you look at the layers, you can see that they go from like nice flat layers, and then they'll turn into kind of these folded, deformed shapes during this collision. All right, another animation just to show you what I'm talking about. So let's say you take an igneous rock like granite. Granite has feldspar, quartz, biotite, amphibole, these other minerals in it. Let's say you take that granite, you push it underground, you expose it to high temperature and high pressure. That pressure and that heat squeezes all the minerals. They start to form this banding, and they will align into what we call foliation, linear light and dark banding, due to that heat and pressure over time. So just a couple rock names that we'll talk about here. I drew some arrows here just to remind you that this is the collision of two tectonic plates and it's pushing up mountains. If you find a rock in that environment that is close to the surface, it's called slate. Slate tends to be the least deformed because it is the closest to the surface. It's been subjected to the lowest temperatures and the lowest pressures. Let's say you find a rock that's a little bit deeper down, then you get something called a phyllite that will form. It's pretty shiny metamorphic rock that will form. Again, it's subjected to higher temperatures and higher pressures. Let's say you take that same rock, push it a little bit farther down, you get something called schist. These are German words here. So you get something called schist. It'll have a little bit more foliation or layers to it and a little bit more banding of light and dark. Then lastly, if you have a rock that comes from the deepest down, you have the highest degree of deformities, and you get these light and dark bands in a rock that we call gneiss. So just to give you an example of common uses for these individual rocks, slate is commonly used for building materials. So roofing is made of slate, and then chalkboards are also made of slate. And then just to show you another example of kind of what a gneiss looks like. So here's just some of the banding, the light and dark banding. So it's been subjected to the highest temperatures. and the highest pressures. All right, so you should have another quiz question to answer, and then you'll still come back after that one. Again, just reiterating the origin of rocks and where rocks can form. So we've put all of them together now at this point where igneous, metamorphic, and sedimentary rocks can form. Then the last thing that I want to finish up with is the idea of the rock cycle. So the rock cycle is the idea that you can take any rock on Earth's surface and you can turn it into any other rock over time. So the rock cycle is the creation and the destruction of the three rock types. So you can take a basalt from lava, and through certain processes, you could turn it into sandstone. Or you could take sandstone, and through certain processes, you could turn it into basalt. You could take basalt, subject it to metamorphism. You're going to get gneiss. Let's say you take gneiss, you can turn it into basalt. Or if you take gneiss, you can turn it into sandstone, and vice versa. So the idea of the rock cycle is you can take any rock on Earth, you can turn it into another rock if you give it the right processes in enough time. So your final question here is basically to use this diagram. So this is an illustration of the rock cycle. You got sediment, you have sedimentary rocks, metamorphic rocks, magma, and igneous rock. And your job is to match each letter to the process that would describe the transformation from one to the other. So I've already given you an example. So let's say you're looking at how an igneous rock can turn into magma. In order to take an igneous rock and turn it into magma, it just has to melt. So that would be an example of that. I'll give you one more example. So let's say you have magma and you're going to turn that into an igneous rock. You have to take that magma and it will cool down. If it cools and solidifies, then you're going to get an igneous rock. So that would be your answer for G there. Okay, so at this point you should be good to complete the quiz, but again, you can pause it here if you need to look at this diagram while you answer the quiz question.